Hello, and welcome to another lecture. So this is on Rouché's theorem, which is subsection 5.4.2 in the book, and you can get the book in the link in the description. All right. So the idea of Rouché's theorem is that two holomorphic functions that are close on a cycle, that whose values are close on a cycle, have the same number of zeros inside the cycle, right? It's the vague idea of it. And if we have a meromorphic function, if we're allowing poles, then it's not that it has the same number of zeros and the same number of poles, but the difference between zeros and poles is the same. So, some examples. So, for example, z squared, holomorphic function, it has two zeros counting multiplicity at 0. And z minus epsilon, z plus epsilon is very close to z squared on the circle. And yeah, it still has two, as long as epsilon is small, right? And it still has two zeros, right? One at epsilon, one at minus epsilon, right? Now, similarly, the function 1 and the function z minus epsilon, z plus epsilon, the difference between the number of zeros and the number of poles is the same. So 1 has no zeros and no poles. So the difference between their number is 0. Z minus epsilon divided by z plus epsilon, well, it has one pole and one zero. So their difference is 0. So yeah, it's the same. And these functions are close on the circle, right? So that's the basic idea, right? So let's write down the term, right? So suppose that we have an open set in the complex plane. We have a cycle in U that's homologous to 0. So recall that means that it does not wind around any point in the complement of U. So it doesn't wind around the outside of U. And let's also suppose that it doesn't wind around anything more than twice, right? So the winding number is either 0 or 1 for everything not on gamma, right? So clearly it's 0 for when z is not in U, but it's the only points that it winds around, which are going to be in U, it winds only once around them, right? And so then we can think of all the points that it winds around as the inside of gamma. All right. And suppose that we have two meromorphic functions, f and g, right? And let's suppose that they have, none of their zeros or poles are on G, right? So all their zeros and poles are somewhere off of G, right? And suppose that you have this inequality. The difference between f and g, so the difference between their values, is strictly less, and that's an important thing, that it is strictly less. That their difference, the difference of the values is strictly less than the modulus of the sum of the moduli of the numbers, right, of those values, right? For all, this just on gamma, so just on that cycle that we're interested in, right? And it's important that this is strict inequality, right? Let's give a name to the inside, right? So let's call it V. So those are all the points that gamma winds around. And let n sub f and n sub g be number of zeros counting multiplicity inside V of f and g respectively, right? So n sub f is the number of zeros in V, just inside gamma. Counting multiplicity of f, and n sub g is the same thing for g, right? And p sub f and p sub g those are the poles, right? So p sub f is the number of poles of f, p sub g is the number of poles of g in V, counting multiplicity, right? Then, yeah, we get that the difference, these differences of the zeros and poles are the same for f and g. Now, there's a simpler version if we just assume holomorphic, right? So suppose that U, gamma, and V are the same as above. So we would just be doing the same thing, right? So that's the same thing as in the Rouché theorem. But now suppose that F and G are actually holomorphic. Suppose that they don't have any poles. And now you don't have to worry about these, checking if these zeros are on gamma, because we're going to assume this inequality, and it's a strict inequality, and it cannot possibly hold if F and G has a zero, right? So that makes the statement simpler. If you get the strict inequality on gamma, then F and G have the same number of zeros, counting multiplicity again, right? So that's the simpler version for holomorphic functions, right? And it makes it a little bit easier to apply. All right. Now, the classical statement of the theorem is actually this guy, right? Well, the inequality in the classical statement. So it's basically missing the plus. This is terrible for writing, right? Plus the modulus of G, right? So that's weaker, right? So, but it has a nice interpretation, right? And it has a nice interpretation in terms of sort of, if you keep thinking about the argument principle, right? It's really the number of zeros is the number of times you wind around zero. Well, think about F as being like, suppose you're walking your dog and you walk around a tree a number of times. Like, let's say you walk about 3 times around the tree, right? In the positive direction, right? And you're maybe not in a circle, right? But your distance from the tree is the modulus of f of z, right? That's how far, and you're walking around in the complex plane, right? The tree is at the origin, right? And you're walking around, your distance to the origin is the modulus of f, right? Now, the dog is another holomorphic function, right? The dog is g, right? And what you're assuming is that the distance that your dog is away from you is strictly less than how far you are away from the tree. And so as you walk around, there's no way that the dog, it can be very far away from the tree, but there's no way it can sort of like go around the tree, right? You're keeping it always, you're further away from the tree than how far your dog is from you, right? And so basically the Rouché's theorem is that it says if you walked around the tree 3 times, your dog walked around the tree 3 times. That's basically one of the proofs of Rouché's theorem, right? The visual proof of Rouché's theorem. All right, so let's prove it, right? So let's take the more general one, right? The modulus of f minus g strictly less than modulus of f plus modulus of g, right? Well, and there's something else we did, right? I divided by g, right? So we have this inequality on gamma, right? Now, it's really about just this function f over g, right? And that function is never negative. Well, that follows from this inequality. I have a function, right? For z on gamma, neither f or g has a 0 or a pole, right? So this is a perfectly, holomorphic function on gamma, right? So we have just some number, and you can just sort of convince yourselves that if the distance of that number from 1 is strictly less than 1 plus the absolute, the modulus of that number, then you cannot be negative, right? That number cannot be negative, right? It can be anything else in the complex plane, but it cannot be negative. It cannot be 0 either, right? So, all right, so that means that f over g is never negative, right? It's valued in the slit plane, that's the complex plane minus the negative real axis, right? That's where it takes its values. It doesn't take its values anywhere else. Now, on the slit plane, on this guy, we can define the logarithm, right? The principal branch of the log, let's say, right? I mean, that is a simply connected domain. So we can define a branch of the log. We actually have the principal branch is sort of the default branch of the logarithm, right? So now let's take that, right? That's a nice holomorphic function now, right? Normally log is not holomorphic. Now we have log as a holomorphic function, well, on this domain. Well, and then if the log is the holomorphic function here, if I compose it with phi, this f over g, right? Well, that's never negative, so phi is valued in the domain of the principal branch of the log, and its derivative is phi prime over phi, right? So phi prime over phi has an antiderivative, right? In some neighborhood of gamma, right? Maybe not everywhere, but in some neighborhood of gamma. All right. Well, that means we can now apply Cauchy's theorem for derivatives, right? I mean, it is a derivative after all, right? So, well, it's really, just take the antiderivative, apply it at the beginning and the end point. That's the same point, right? So you get 0, right? So you get that this is true, right? And the integral of phi prime over phi around gamma is 0. Well, if you compute what what that is, I mean, f phi is f over g. So a little bit of computation gives you, well, that's what it is, right? That's a little bit of calculus. All right, well, if that's what it is, well, we can write that as 2 integrals, right? We can integrate the f prime over f, and we can integrate the g prime over g with a minus sign in the middle. Now, apply the argument principle, right? Now we have this meromorphic function. We have a gamma that's homologous to 0, right? None of the poles are zeros, or f or g are on gamma. Bang! I get the argument principle tells me that the first guy, that's the number of zeros of f in v, which is inside of gamma, minus the number of poles, right? And the second integral is, well, the same thing for g, right? Which is precisely what I wanted, right? Wanted to show that these two numbers are equal, right? So that's the that's Rouché. That's the proof of Rouché's theorem, right? So it's it's again it's all like it's like a residue theorem, right? Residue theorem proves argument principle proves this, right? And I guess Cauchy's theorem for derivatives, and the whole setup here is really this sort of that the dog never went further away from you than well, this is the more complicated inequality, but it's sort of the same idea. All right, so this is basically it's when you look at how this winds around, it can sort of never wind around the 0, right? When I look at phi. All right. So for applications, it's actually this guy is sufficient, right? If you prove this inequality, you don't have to prove the strong inequality. Prove this inequality, right? If this is true, then the you know the other inequality is also true, right? So this is fine. This weaker theorem is sufficient, right? All right. So let's suppose that we have. Let's do something that we know how to do. So let me excuse this first, right? Let's do something that we know how to do, but let's do it using Rouché's theorem, right, as an example. So we know that the zeros of z to the n plus 1 are, well, those are basically the units, roots of unity, essentially. And so they're all on the unit circle, right? Well, let's see how to do that with Rouché's theorem, right? Suppose that we didn't know that. Suppose that we couldn't solve this explicitly. Right, and let's show that all the zeros are on the boundary of the unit circle. Why are we doing that? Because it's simple, right? But it sort of demonstrates the idea, right? So on a slightly smaller circle, right? So I look at a slightly smaller circle of radius 1 minus epsilon, right? Still centered at the origin. Then if I take, I guess this is slightly flipped around, take p minus 1, right? So p would be my g and 1 would be my f, right? But p minus 1 is e to the n. The absolute value of that is the absolute value of, right, the modulus of z to the n. And because we're on this slightly smaller unit circle, that's less than 1. 1 minus epsilon is less than 1. So, well, that's equal to the modulus of 1, right? So we have, if f is 1 and g is p, we're satisfying this inequality, right? And therefore, the number of zeros of the polynomial 1 is the same as the number of zeros of the polynomials p inside this smaller circle, right? So what it says is that there are, because this is for every epsilon, so there are no zeros in the unit disk, right? On the other hand, if I take a slightly bigger circle of radius 1 plus epsilon, right? And now for f, I use z to the n. That's another way. Basically, I'm using, one of my functions is one where I know the number of zeros, and one of them I don't know, right? So I don't know where the zeros of p are. Well, let's suppose that I don't know. And I know where the zeros of z to the n are. They're all at 0, right? I have n zeros at 0, right? And so I take a look at the difference, right? Well, that's just 1, right? And that's strictly less than the modulus of z to the n, because we are on this circle of radius slightly bigger than 1, right? 1 plus epsilon, right? So the modulus of z to the n is 1 plus epsilon to the n, right? So still slightly bigger than 1, right? Or, strictly bigger than 1. That's the point, right? We get a strict inequality. So by Rouché, p and z to the n have the same number of zeros inside this disk of radius 1 plus epsilon for every positive epsilon, right? Well, that means that, all the zeros have to be on the unit circle. There are n zeros that this guy has because it's degree n, right? So all of its zeros are inside this disk for every epsilon, and they're never in the unit disk. Therefore, the only place that they can be is on the unit circle, right? So this is a typical application of Rouché's theorem. Now, let's look at a slightly more complicated one, just so you don't say, well, we can only locate these zeros for really trivial examples. Let's do slightly less trivial example. Suppose that I have this you know, quartic polynomial. Now there is a quartic formula. That's annoying, right? So let's not use it, right? So it's still something that I could figure out, differently, but it's more complicated. That's my point, right? And of course, you could use it in even more complicated setups, right? All right. So, but it's definitely not clear immediately what's going on here, right? But let's take this look at this P, right, on the unit circle, right, and let's subtract this. So basically, I'm subtracting away this and this, right? So I'm left with this guy, and I'm on the unit circle. Now I just use triangle inequality, sort of this sort of brute force approach, right? Just do this, and well, mod z is 1 on the unit circle, right? So this is just 12 plus 4 plus 6, which is 22, right? Which is strictly less than 23, right? Which is what this guy, this is, right? Well, that's just a funky way of writing 23 if z is on the unit circle, right? And by inverse triangle inequality now, this is precisely, or less than or equal to, precisely the thing that I subtracted, right? So I have, applying Rouché's theorem, what I get is that the number of zeros in the unit circle, so inside the unit circle, so number of zeros of P is the same as the number of zeros of this thing, right? Because there was this strict inequality over here. Now, this guy is easy to solve, right? Because, well, I can just factor out the z squared. I get a, I just get a quadratic, actually really simple quadratic. I can just take the square root. Zeros, those are at plus or minus square root of 24 times I, right? Whatever that is. It's definitely outside the unit disk. Quite a ways outside. So it has 2 zeros there, and then it has 2 zeros at the origin, right? The z squared, right? So that means that it has 2 zeros inside the unit disk. So P has 2 zeros inside the unit disk. Now let's look at so it has 2 zeros inside the unit disk. Let's do one more thing. Let's see. Let's suppose that I want to know some big circle where they're all inside that circle, just so that I don't have to look too far out, right? Well, in this case, they're actually all going to be within modulus 46. At least that's what I'm showing here. So suppose that I look at the circle of radius 46 plus epsilon, and I subtract z to the 4th, right? Which has four zeros inside that circle, right? They're all at the origin. Well, so if I subtract that, I just get all the other terms, right? And I again do this sort of really stupid estimate, and I will get I'll get a strict inequality because mod z is 46 plus epsilon, right? And so I'm gonna get this strict inequality over here to go to z to the 4th, right? So I have now that z to the 4th and p have the same number of zeros inside the circle of 46 plus epsilon, right? So all 4 zeros satisfy this inequality, basically. That's what I've proved, right? So I've located them at least, at least a little bit, right? Now, actually, if you solve this thing, the largest zero has modulus less than 10. I can't remember what it is. I did solve the thing, right? So I didn't get the perfect estimate over here. Yeah, but I got some estimate, right? In a fairly simple way, right? I mean, this is just, you know, triangle inequality-ish estimate, right? I mean, there's nothing too complicated here, right? And I got a bound on all of the zeros, right? They are all within there, right? All right. So so those are, you know, just a couple of sort of, those are the typical applications, typical sort of things that appear on exams because they're the easy thing to ask, right? Easy applications of Rouché. All right. So next time, what we're going to look at is Horowitz theorem. So this is looking at what happens to zeros as if you have holomorphic functions that approach other holomorphic functions, right? What can happen, right? So if you have a holomorphic function as a limit of a sequence of holomorphic functions, uniformly on compact subsets, right? So that's Horowitz. So we're going to do that next time. Okay, so see you then.